What are paradoxes? Like Frederick and Flocky here, you may have seen our Paradoxical Paradoxes playlist, where we cover all sorts of mind-boggling oddities. After exploring some of these paradoxes, we thought there must be some kind of classification scheme for them. It must be possible to group similar paradoxes together. In fact, it is. Follow us through this video as we explore 5 different types of paradoxes and examples for each type. We'll start easy before we tackle the really mind-blowing ones. Stay tuned! Type 1. Philosophical Paradoxes, introduced by Flocky. We call a paradox philosophical if it is a thought experiment that leads to seemingly unresolvable results. Note that we do not mean unresolvable in a moral sense, as in moral dilemmas, but unresolvable in a logical sense. A good example of a philosophical paradox is the grandfather paradox. Imagine time is a straight line, starting in the past and pointing to the future. Somewhere precisely defined on this timeline, there are 3 distinct events. First, your parents meet, beginning the long-lasting relationship they have developed over time. Second, Mr. and Mrs. Flocky are not only happily married, but become the proud parents of our beloved Flocky. Third, the present day. Flocky has grown up and is busily working on his big invention. A time machine that will allow him to travel back in time. After successfully building this time machine, Flocky uses it to travel back to the exact moment when his parents met. Unfortunately, he interacts with his parents in such a way that they never get to meet each other. This affects the future. His parents will not be together when he is born, which means that he will not be born at all. And if Flocky is never born, he cannot exist. But then he cannot travel back in time to prevent his parents from meeting. It's a paradox. Usually the story is told in a slightly different way. The protagonist travels back in time to meet his grandfather and prevents himself from being born. Hence the grandfather paradox. There are several possible solutions to this paradox. It could be that traveling back in time is impossible. From relativity, we know that traveling into the future is technically possible. It could also be that there are multiple timelines, but the most important and our favorite solution is this. Flocky is too gentle of a spirit to do something like that. Regarding time travel, my favorite paradox can be phrased as the following question. If I start building a time machine right now and promise myself to send the blueprint of the finished machine to this very moment if I succeed, have I failed if I am not instantly finished? Think of it. If I'm successful, I will send myself the blueprint into the past, but then I do not have to invent the machine because I instantly had the blueprints for it. The invention would just appear without any clear origin. This thought experiment is sometimes referred to as the bootstrap paradox. Let's look at another philosophical thought experiment. Theseus' boat or Theseus' paradox. Flocky is a big boating fan and is very proud of his little boat, which he affectionately calls Flocky's ship. Over the years, more and more parts of the ship had to be replaced. Come to think of it, all the parts have been replaced at some point. Flocky himself has a strange feeling about this and playfully likes to call his boat Flocky's ship? ? Somehow it does not feel at all like his original little boat. Is it even the same little ship he bought all these years ago? His ship? This thought experiment can be taken even further. Imagine cheeky Rex is seen in the distance. He has collected all the old parts of Flocky's original ship and has built his own boat using these parts. Which of them is now Flocky's boat? Was there a time when Flocky's original boat stopped being his? And if not, does Rex's boat still belong to Flocky? But then whose boat is Flocky in at this very moment? Or does Flocky own 2 ships now? Very thought-provoking ideas indeed. But enough of the fun, let's look at some more serious paradoxes. Type 2. Veridical Paradoxes. Introduced by Kitty, Veridical paradoxes are statements that seem to be false but are actually proven to be true. In fact, these paradoxes can seem so unlikely that some people refuse to believe them outright, even though they can be proven to be true without a doubt. Our first veridical paradox is the birthday paradox. Kitty still remembers last year when Flocky celebrated his birthday and, to everyone's surprise, challenged his guests with a probability riddle. Let A be the proposition that two people in the room celebrate their birthday on the same day of the year. Then we can make two trivial statements. If there is only one person in the room, then the probability that two people share a birthday is 0, since there is no second person. Hence, P of A given one person equals 0. On the other hand, if there are 366 people in the room, since there are only 365 days in a year, at least two of these people must share birthdays. Hence, P of A given 366 people equals 1. Somewhere between these two special cases, there is a group of X people such that the probability of two sharing birthdays surpasses 1/2. Imagine Flocky's party. How many people must attend the party such that the probability that two of them have the same birthday is greater than 1/2? The answer is 23. I bet you did not expect this result, but it is true, I swear. If you don't believe us, check out our video about the birthday paradox, which you can find in the info card. If you thought the birthday paradox was a brain teaser, then wait for this one. It is not even a single paradox, but a whole branch of science consisting entirely of veridical paradoxes. Not only that, it also provides the basis for our modern technology like semiconductors. It's our lovely friend, quantum mechanics. There are so many veridical paradoxes in quantum mechanics that it would be impossible to cover them all in this video. But here are a few honorable mentions. The double-slit experiment, Schrödinger's cat, quantum superposition, quantum tunneling, and last but not least, spooky action at a distance, also known as quantum entanglement. Let us take a closer look at the last one. The name spooky action at a distance was infamously introduced by Albert Einstein, who was not a big fan of the idea. At the time, it was debatable whether the strange behavior of the quantum world can be true or not. Today, after many years of experimentation, we know that the world behaves according to the laws of quantum mechanics. A strange world indeed. Imagine a particle with two opposing properties, or states, as physicists like to call them. For simplicity, let us call these properties up and down, as indicated by the arrows. Before we measure the state, we cannot know which of the two it will be. Up and down are equally likely for a given particle. Now here comes the trick. We can manipulate the two particles such that they will always be in opposite states. Suppose we do this for the two particles shown here. Then we move the particles many light years apart. As soon as we measure the first particle, the quantum state of the second particle instantly collapses to the opposite state of the first one. Almost as if the second particle knew that the first one was being measured. And not only that, but the communication takes place instantly, seemingly violating one of the most fundamental laws of the universe, that no information can travel faster than the speed of light. Without getting too deep into quantum mechanics, this apparent violation of the speed of light can be resolved. There is no violation because we first need to move the two particles away from each other, which is limited by the speed of light. The fact that the collapse for the second particle happens instantly is a fundamental law of nature that we have to accept, even if our brains have not evolved to think about it intuitively. Basically the definition of a veridical paradox. If you would like more videos on quantum mechanics, let us know in the comments. Okay, I can't say it's going to be more brain melting than quantum entanglement, but here's another good one. The Monty Hall problem. Rooted in a game show, imagine that Kitty is the host of this show and Leon is the playing guest. There are 3 doors. Behind 2 are goats, and behind 1 is a brand new sports car. Obviously, Leon wants the car. Kitty tells Leon to choose a door and he quickly chooses the middle one. Kitty then opens one of the remaining doors, which contains a goat. In this step, Kitty will never open the door with the car behind it. Now comes the crucial question from Kitty. Leon, do you want to reconsider your decision and change the door? What should Leon do? Once again, it is a question of probability, and if it were not for quantum mechanics, I bet probability theory would be the branch of science with the most veridical paradoxes. The answer is yes. Leon increases his chances of winning if he decides to change doors. We also made a video about this paradox a long time ago. Check out the info card and have a look if you want to dive deeper into this. The last veridical paradox for today, 0.999 repeating equals 1. I do not even know what to say about this. It is true. We made a video about it with 6 different arguments about why this is true, at least 3 of which count as formal proofs. But no matter how many formal proofs there are, people, not mathematicians, but people, still refuse to accept this fact. A textbook example of a veridical paradox. Please see the info card for our comprehensive video on the topic. Well done if you have made it this far. I wish I could say that it gets less mind-scratching from here, but I'm not gonna lie. Type 3 paradoxes are Falsidical Paradoxes. Introduced by Leon, these paradoxes are statements that not only seem to be false, but are actually false. Seems trivial, you think? Wait for the examples, because the first one completely broke the popular internet maths scene a few years ago. The sum of all natural numbers, 1 plus 2 plus 3 plus 4 and so on, equals -1/12. Of course, this equation seems ridiculous, and to take away the final result, it is wrong. But there are several different ways to get the result -1/12 for this sum. In fact, -1/12 is very unique, because it is the only definite value that can be associated with this sum. Furthermore, in some branches of physics, this sum is actually associated with the value -1/12, and the results, as well as the respective observations, fit well together. A few years ago, the popular YouTube channel Numberphile posted a video on the subject in which they perhaps exaggerated the association of -1/12 with this sum, stating that it was actually equal to -1/12, which sparked a huge debate among maths enthusiasts. To resolve the matter, in mathematics, for an infinite sum to be equal to a finite value, 2 things must be given. Association with a unique finite number, that part we have given here, and convergence of the sum to that unique finite value. Trivially, the convergence is not given, and only the association remains. We have made a humorous video on this topic. Please watch it if you like. As usual, you can find it in the info card. One final note. This property of an infinite sum being associated with a unique finite number but not having any convergence occurs quite often. The sum of all natural numbers is not unique in this regard. Let's lighten the mood with a second Falsidical paradox. 2 equals 1. Please hand Leon a blackboard. Let us start with 2 real non-zero numbers a and b, where a equals b. Multiply both sides by a, yielding a squared equals ab. Subtract b squared from both sides. Factor out a minus b on both sides. Note that we are using a binomial formula on the left-hand side. Now cancel a minus b, giving a plus b equals b. But remember what we started with. A equals b, so b plus b equals b, and therefore 2b is b. Now cancelling b leaves us with 2 equals 1. Quod erat demonstrandum. There are many similar proofs for 2 equals 1 or 1 equals 0 or something like that. Not surprisingly, these proofs not only appear to be false, but are in fact false. Classical Falsidical Paradoxes. In this particular case, we have hidden a division by 0 somewhere in the calculation. Perhaps Marcus, the little bird, has indicated whether he has found this tiny blunder? Here is our favorite from university, the complex unitary triangle. Let us draw a complex coordinate system with the real numbers on the x-axis and the complex numbers on the y-axis. Let us also set the scale with the numbers 1 and I. Now we can draw a triangle with the lengths I and 1 in our coordinate system. As usual, we label the long side with the letter C. But how long is C exactly? According to the Pythagorean theorem, we have c squared equals a squared plus b squared, which in our case means c squared equals 1 squared plus I squared. 1 squared is 1 and I squared is minus 1, so c squared equals 1 plus minus 1. But then c squared equals 0? How can this length be 0? We can clearly see that the line has a length that is not 0. The solution to this one we will not reveal here. Discuss it in the comments. Let us conclude the Falsidical Paradoxes with a true classic from the ancient Greeks, Zeno's paradox. As we all know, Rex loves apples, so as soon as he sees the delicious apple, he runs straight for it. But before Rex can reach the apple, he has to go half the way. But before he can go half the way, he has to go a quarter of the way, and 1/8 of the way before that, and 1/16 of the way before that. In fact, before Rex reaches his tasty apple, he has to go an infinite number of little ways, all of which are not equal to 0 in length. The ancient Greeks argued that an infinite number of ways that are not equal to 0 cannot lead to a finite result, so it cannot be possible for Rex to reach his apple. Usually, Rex reaches the tasty apple in the blink of an eye, and we see that the ancient Greeks were wrong. As it turns out, after applying advanced mathematics, a sum of infinite non-zero quantities can in fact be finite. Fun fact: the video on Zeno's paradox was one of our first ones. Check out the info card if you're interested. Also, note the difference in quality from then to now. All for the fans. I think that is enough for the Falsidical Paradoxes. Let us continue with the purest form of paradoxes. Type 4. The Logical Paradoxes. Introduced by Frederick Foxington, these paradoxes are statements to which no truth value can be assigned. We do not mean that no truth value can be assigned because the statement is subjective, but because the statement is a self-contradiction. Since the release of Portal 2, this first example has lost much of its power, because everyone knows it, and also GLaDOS could not be defeated with this paradox. This statement is false. Think about this for a moment. If we take the statement to be true, then according to what the statement says, it must be false. This is a contradiction, so the statement must be false, right? But if it is false, then it tells the truth about being false, which means it is true. As already explained, these are the purest paradoxes there are. There is no solution. The statement is a self-contradiction, and it is not possible to assign a truth value. Let's see a more fun example of basically the same paradox. Leon loves to dress up as Aristotle for Halloween. He always goes around telling everyone that he knows nothing. He is the man who knows no things and answers all questions accordingly. Apart from Frederick, none of the other party guests ever got the clever joke in this statement. If Leon really knows nothing, then this statement is true, and he at least knows that he knows nothing, which means that he knows one thing, which contradicts the original statement. So Leon's statement cannot be true, but if the statement is false, then he must know something, but he is unable to answer any questions truthfully, which means that he actually knows nothing. At least Frederick was able to appreciate not only Leon's commitment to his costume and role, but also our commitment to drawing Leon as Aristotle. Less fun, but more baffling, is the infamous Russell's paradox. Originating from set theory, this is a really hard problem to solve. Consider the set of all sets that do not contain themselves. It's a huge set. Now the question is, does this set contain itself? Let's do a case analysis. Case 1. The set does contain itself. But then the set cannot be part of itself, because the original set only contains sets that do not contain themselves. So case 2 must be true. The set does not contain itself. Wait a minute. If the set does not contain itself, then it must be part of itself, because every set that does not contain itself must be part of the set. If you do not want to end up like GLaDOS, do not think too much about this. Instead, let us finish with some paradoxes that are easier on the brain. Type 5 paradoxes are what we call honorable mentions, playfully presented by Rex. These are just a few other uses of the word paradox that we came across in our research and wanted to share with you. Firstly, there are visual paradoxes, which are shapes that can be drawn in one space, for example, two-dimensional space, but would be impossible in a higher or lower dimensional space. For example, look at this triangle. This is a shape that can be drawn on paper, but cannot exist in 3 dimensions. The Möbius strip and the Klein bottle are also interesting to mention when speaking of special objects. These 2 shapes have very intriguing dimensional properties as well, but we would not really classify them as paradoxical. Another fun use of the word paradox are linguistic paradoxes. When Leon dresses up as a Greek philosopher, apart from not knowing anything, he likes to hide deeper truths in paradoxical statements. For example, he uses phrases like "less is more" when he wants to communicate that simplicity or minimalism is more effective and valuable than excess. Almost the same meaning can be found in the phrase "subtract to add." Similarly, Simon and Garfunkel called one of their hit songs "Sound of Silence," popularizing a very intriguing linguistic paradox. We come to the end with the last type 5 paradox, medical paradoxes, or more specifically, paradoxical reactions. These occur when your doctor prescribes a drug for a particular type of symptom, but your body responds by making the symptom even worse. Fortunately, these problems are very rare. Besides, I hate swallowing pills. After unraveling this final paradox, we have reached the end of our video. If you enjoyed watching, please consider showing us some love by leaving a like or sharing your thoughts in the comments. We really like engaging with you, the Science Gang community.